Well, let's see. We've just developed a fairly plausible program for computing the derivatives of algebraic expressions. It's an incomplete program. You would like to add more rules, and perhaps you might extend it to deal with uses of addition with any number of arguments and multiplication with any number of arguments, and that's all rather easy. However, there was a little fly in that ointment. We go back to this slide. We see that the expressions that we get are rather bad. This is a rather bad expression. How do we get such an expression? Why do we have that expression? Well, let's look at this expression in some detail. Let's find out where all the pieces come from. As we see here, we have a sum, just what I showed you at the end of the last time, of x times 1 plus 1 times x. That is the derivative of this product. The product of a times that, where a does not depend upon x and therefore is constant with respect to x, is this sum, which goes from here all the way through here and through here, because it is the first thing times the derivative of the second plus the derivative of the first times the second, as the program we wrote on the blackboard indicated we should do. And of course, the product of bx over here manifests itself as b times 1 plus 0 times x, because we see that b does not depend upon x. And so the derivative of b is this 0, and the derivative of x with respect to itself is the 1. And of course, the derivative of the sums over here turn into these two sums of the derivatives of the parts. So what we're seeing here is exactly the thing I was trying to tell you about with Fibonacci numbers a while ago. That the form of the process is expanded as from the local rules that you see in the procedure. That the procedure represents a set of local rules for the expansion of this process. And here the process left behind some stuff, which is the answer. And it was constructed by the walk it takes of the tree structure, which is the expression. So every part in the answer we see here derives from some part of the problem. Now, we could look at, for example, the derivative of foo, which is ax squared plus bx plus c, with respect to other things. Like here, for example, we can see that the derivative of foo with respect to a. And it's it's in fact the identical algebraic expression, except for the fact that these zeros and ones are in different places. Because the only degree of freedom we have in this tree walk is what's constant with respect to the variable we're taking the derivative with respect to, and what's the same variable. In other words, if we go back to this blackboard and we look, okay, we have no choice what to do when we take the derivative of a sum or a product. The only interesting place here is the expression. Is the expression the variable, or is the expression a constant with respect to that variable for very, very small expressions, in which case we get various ones and zeros, which if we go back to this slide, we can see that the zeros that appear here, for example, this 1 over here in the derivative of foo with respect to a, which gets us an x squared, because that 1 gets us the multiply of x and x into the answer. That one is 0 over here when I'm taking the derivative of foo with respect to c. But the shapes of these expressions are the same. See all those shapes? They're the same. Well, is there anything wrong with our rules? No, they're the right rules. We've been through this one before. One of the things you're going to begin to discover is that there aren't too many good ideas. Right? When we were looking at rational numbers yesterday, the problem was that we got 6/8 rather than 3/4. The answer was unsimplified. The problem, of course, is very similar. There are things I'd like to be identical by simplification that don't become identical. And yet the rules for doing addition and multiplication of rational numbers were correct. So the way we might solve this problem is do the thing we did last time, which always works. If something worked last time, it ought to work again. Is change the representation. Perhaps in the representation, we could put in a simplification step that produces a simplified representation. This may not always work, of course. I'm not trying to say that it always works, but it's one of the things, one of the pieces of artillery we have in our war against complexity. You see, because we've solved our problem very carefully, what we've done is we've divided the world into several parts. There are derivative rules and general rules for algebra of some sort, okay, at this level of detail. And I have an abstraction barrier, and I have the representation of the algebraic expressions. List structure. And in this barrier, I have the interface procedures. I have constant. I have things like same var. I have things like sum, make sum. I have A1, A2. I have products and things like that. All the other things I might need for various kinds of algebraic expressions. Making this barrier allows me to arbitrarily change the representation without changing the rules that I've written in terms of that representation. So if I can make the problem go away by changing the representation, the decomposition of the problem into these two parts has helped me a great deal. So let's take a very simple case of this. What was one of the problems? Let's go back to this transparency again. And we see here, oh yes, there's horrible things. Like here is the sum of an expression and 0. Well, that's no reason to think of anything other than the expression itself. Why should the summation operation have made up this addition? It could be smarter than that. Or here, for example, is a multiplication of something by 1. It's another thing like that. Or here's a product of something with 0, which is certainly 0. So we don't have to make this construction. So why don't we just do that? We need to change the way the representation works. Almost here. Make some. To be. Well, now it's not something so simple. I'm not going to make a list containing the symbol plus and things unless I need to. Well, what are the possibilities? If I have some sort of cases here, if I have a numbers, if A1 is a number, and here's another primitive I've just introduced, it's possible to tell whether something is a number. And if number A2, meaning they're not symbolic expressions, then why not do the addition now? The result is just the plus of A1 and A2. I'm not asking if these represent numbers. Of course, all of these symbols represent numbers. Okay? I'm talking about whether the one I've got is the number 3 right now. And for example, supposing A1 is a number, if A1 is a number and it's equal to 0, well then the answer is just A2. There's no reason to make anything up. And if A2 is a number and equal A20, then the result is A1. And only if I can't figure out something better to do with the situation will I construct a list. Otherwise, I want the representation to be the list containing the quoted symbol plus, okay, and A1 and A2. And of course, a very similar thing can be done for products. And I think I'll avoid boring you with them. I was going to write it on the blackboard. I don't think it's necessary. You know what to do. It's very simple. But now let's just see. Let's just see the kind of results we get out of changing our program in this way. Well, here's the derivatives after having just changed the constructors for expressions. The same foo, ax squared plus bx plus c. And what I get is nothing more than the derivative of that is 2ax plus b. Well, it's not completely simplified. I would like to collect common terms and sums. Oh, that's more work. And of course, programs that do this sort of thing are huge and complicated. Algebraic simplification is a very complicated mess. There's a very famous program you may have heard of called Maxima, developed at MIT in the past, which is, 5,000 pages of Lisp code, mostly the algebraic simplification operations. But there we see the derivative of foo with respect to x is at least something I wouldn't take off more than 1 point for on an elementary calculus class. And the derivative of foo with respect to a, well, it's gotten down to x times x, which isn't so bad. And the derivative of foo with respect to b is just x itself. And the derivative of foo with respect to c comes out 1. So I'm pretty pleased with this. Okay. What you've seen is, of course, a little bit contrived, carefully organized example to show you how we can manipulate algebraic expressions, how we do that abstractly in terms of abstract syntax rather than concrete syntax, and how we can use the abstraction to control what goes on in building these expressions. But the real story isn't just such a simple thing as that. The real story is, in fact, that I'm manipulating these expressions, and the expressions are the same expressions, going back to this slide, as the ones that are Lisp expressions. There's a pun here. I've chosen my representation to be the same as the representation in my language of similar things. By doing so, I've invoked the necessity, I created the necessity to have things like quotation, because of the fact that my language is capable of writing expressions that talk about expressions of the language. I need to have something that says, this is an expression I'm talking about, rather than this expression is talking about something, and I want to talk about that. So quotation stops and says, I'm talking about this expression itself. Okay. Now, given that power, if I can manipulate expressions of the language, I can begin to build even much more powerful layers upon layers of languages. Because I can write languages that not only are embedded in Lisp, or whatever language you start with, but languages that are completely different, that are just, as we say, interpreted in Lisp or something like that. We'll get to understand those words more in the future. But right now I just want to leave you with the fact that we've hit a line which gives us tremendous power. At this point we've bought our sledgehammer. We have to be careful on to what flies we apply it. Thank you.